Hey guys, myself Humayun Malik, and our today's lecture is in the continuity of our previous lecture, which was Maxwell equation part 1. And there we have discussed what is meant by divergence of a vector field, and we have also discussed the first two Maxwell equations, which are the Gauss's law in electricity and in magnetism. And in our today's lecture, we are going to discuss the third Maxwell equation, which is Faraday's law. But before that, I want to tell you guys that basically we have two types of Maxwell equations. First is integral form, which is in front of you guys, and the second is differential form. Differential form of Maxwell equation are useful for calculating electric and magnetic field at a single point in space. An integral form of Maxwell equation are useful for calculating the field over an entire region in space. While the integral form is well suited for the calculation of symmetric problems such as calculation of electric field of a charged sphere or a charged cylinder or a charged plane. While the differential form is more suitable for the calculation of complicated numerical problems using computers or for the derivation of electromagnetic waves. These both forms are useful and can be transformed into each other using two mathematical theorems. First is divergence integral theorem and the second is curl integral theorem. And one more important thing, that these Maxwell equation, these differential form of Maxwell equation are the most fundamental form of Maxwell equation, and they are also called microscopic form of Maxwell equation. And these differential form of the Maxwell equations are also known as the macroscopic form of Maxwell equation. And now let's discuss the important terms in our macroscopic form of differential equations. As we know that when we have a del operator with dot multiplied with it, it symbolizes the divergence, and whenever we have a del operator with a multiply sign with it, it symbolizes the curl, and whenever we have a del operator simply multiplying with something, it symbolizes the gradient. In our equation 1, d is the displacement density, and it is directly proportional to the electric field. So in some equations you see that there is del dot E is equal to rho divided by epsilon naught, and that simply these two equations are equal, and where D is equal to epsilon E. By simply putting D is equal to epsilon E, we get the same equation which we often see in different books, that del dot E is equal to rho divided by epsilon naught. So rho is the volume charge density, and in equation 2, B symbolizes the magnetic field, and in equation 4, H is the magnetic field intensity. It tells the intensity of magnetic field. In equation 3, E is the electric field, and in equation 4, J is the current density. Now what is current density? Current density is the current passing per unit area such that I divided by A. And in equation 4, we have the term partial d divided by partial t. This is the displacement current, and this is the current between two plates of a capacitor. Maxwell adds this current with the normal current in Ampere's law of current, and that's why these equations are called modified Ampere's current law. And now let's discuss our today's topic, which is Faraday's law, which is the third Maxwell equation. Well, this equation tells us that how the electric field and magnetic field are linked with each other. So before going to understand Faraday's law, we should know about the curl of a field. Imagine we have a field, and again we are assuming that the length of the arrows actually signifies the length of the field. So you can see that our field is stronger at the top, and as we go down it is decreasing in its strength. If we place a stick in this field, so at the top of the stick, since the field is very strong, it will exert more effect on the upper end than at the lower end. So what will happen is that the stick will tend to rotate, because the effect of the field is more at the upper end as compared to at the lower end, so stick will experience some sort of torque and it will rotate. This is what actually the curl of a vector field signifies. So curl at a particular point in vector field actually represents how much turning effect would it produce if you were present at that point. So now coming back to our Faraday's law, in terms of Faraday's law, imagine you have a round metallic ring and you pass a time varying magnetic field through it. Now what this time varying magnetic field do, it will induce an electric field around that ring, and as a result we have a current in that metallic ring. So in this way Faraday's law actually gave us a relation between change in magnetic field and the induced electric field. Here on the right hand side of the equation, negative sign signifies that the induced current is in such a direction so as to oppose the change in magnetic field. So this was our lecture in which we have discussed the Faraday's law, which is the third Maxwell equation, and in the end I will request you guys to like my videos and subscribe my channel. Thank you guys. Khuda Hafiz.